Okay, I think we can kick off. So first of all, thank you everyone for joining for the webinar for the power of AI in engineering simulations using Odyssey. Mijn naam is David Meesaros, and I'm a technical consultant at Insuma Innovation, and we are very happy to welcome you. Today I'm here with my colleagues Kambis Kamantas from Hexagon Design and Engineering, the Senior Director for AI and Machine Learning. And together today we also have Naima Gerings with us, who is our Marketing and Sales Enablement Manager. And we are very happy to welcome you. And as mentioned before, if there are any questions, please feel free to ask them in the Q&A section. And we will answer these questions at the end. And as mentioned also before, this session is recorded and it will be shared at the end of the webinar. So to kick off, I would like to start with the presentation. So today we are going to talk about artificial intelligence and machine learning. And I think if you are on LinkedIn or even on other social media platform, you can see that artificial intelligence and machine learning is still a quite hot topic. It has been started a couple of years ago, really, but it's still becoming more and more used in our everyday lives. So for example, if you think about ChatGPT, I'm sure some of you are using it, for instance. But I think what is important is to consider also, okay, this sounds pretty interesting for me, this AI, and this sounds very fancy and cool, but what is the actual essence? How can we actually utilize this? How can this be actually utilized? And in today's webinar, what I would like to dive into is to basically showcase to you the power of artificial intelligence in engineering simulation specifically. And therefore, I would like to use Odyssey, which is Hexagon's artificial intelligence and machine learning software. So before we completely kick off, first, I would like to introduce you to Insuma and Hexagon portfolio. Then after that, we will go into what is actually Odyssey. Some of you might have heard from this before, some of you might not, but therefore we are going to just, in a general overview, discuss this. Then we will go into reduced order modeling from a helicopter overview. What is it basically, where it can be used, and what are the benefits? After that, I want to showcase to you 3 case studies whereby Odyssey has been used. Then after that, we dive into 2 demonstration examples, one with Adams and the other one with Cradle CFD. And after that, we will conclude our presentation. And at the end, if there's time, then we will try to answer some questions. So first of all, as I mentioned before, we are from Insuma, and we are an exclusive business partner of Hexagon in the Benelux region. We are mainly focused on design and engineering, and we are providing second-line support and engineering services. And we have in various engineering industries, would it be aerospace, automotive, or even medicine. And we have more than 90+ customers in the Benelux alone. So, that's not it. Yes. So just to give an overview, the world of engineering simulation is quite broad, as you might know. And yes, Hexagon offered multiple solutions to different engineering disciplines alone. For example, we are also located in the multiphysics, and especially my personal favorite is Cradle CFD. That is one of the solutions which we use, for example, for fluid dynamics and heat transfer, but also in system dynamics, such as for Adams and Romax, and also in virtual manufacturing and material science as well, but also in artificial intelligence and machine learning. And as I mentioned before, today we will mainly focus on artificial intelligence and machine learning using Odyssey itself, but we will still try to couple it with different kind of simulation software. So in this case, we will look at Cradle CFD, as I mentioned before, and also from the system dynamics perspective for Adams. So just to dive into the nitty-gritty, some of you have heard about this before, I assume, but some of you have don't. But what is Odyssey technically? Odyssey is basically a tool specifically designed for the engineers, and this is mainly to help them in the design of experiment activities, and also to help them during their, let's say, optimization activities. This is, of course, very, very broad. This can mean anything. So the idea behind Odyssey is that it is very, very versatile, and it can be used in multiple engineering disciplines. So it's not necessarily discipline bonded, but it can be used in different kind of applications, whichever you have, basically. Predictive techniques are utilized in Odyssey. And what I mean by that is basically the machine learning algorithms use data sets basically to enable a quick and easy data manipulation in order to obtain, for example, a new response for your design. Or, for example, to obtain a new optimized case that you are looking at. Hereby, engineers especially can avoid the basically costly manual labor, if I may say. So what I mean by that is if there are possibilities or if there is work and tasks where, for example, large amounts of data has to be generated, and that takes a lot of time because you have to constantly change the parameters yourself, Odyssey can help basically in that to do that automatically. So technically, just to underline this, the main challenges which Odyssey can cover are usually inefficient design process, so something that takes a lot of time, and of course the higher costs which are coming with that. But I would say Odyssey is a constellation word, if I may call it like that. And what I mean by that is that Odyssey exists of multiple sub applications / plugins. And these are all visible on the screen right now. So what we can see is that we have 5 different applications whereby 2 are plugins. First of all is we have Odyssey CAE. Odyssey CAE is basically a program, a tool at least, which is used, for example, for real-time predictions for a certain for a certain set of design space, so for design of experiments. This can, for example, help in multiple scenarios, which we will see also later in the demonstration, whereby we have multiple variables which are basically somehow connected together, but still there's an optimization or an optimal setting to be found. Therefore, it can be also used for robustness studies, sensitivity analysis, and, for example, also reliability analysis as well. On another note, we have Odyssey AI. Odyssey AI is basically it's more focused technically on image-based prediction. So let's say if I have a data set of pictures and I know from those pictures what is, for example, wrong and what is, for example, right, I can then import it in my learning database, and every single new picture, and for that matter, are predicted based on your learning database. But this is not only bonded to pictures, obviously. This can be, you can obviously use, for example, different CAD geometries, but also sound. And the actual benefit of this is that it is very tailor-made. So you can create your own customized setup for that specific case that you are working on. Then after that, we have Odyssey Solver. And Odyssey Solver, I would basically consider it as the engine of the actual Odyssey constellation itself. So basically, this is what, for example, is being used in different applications, such as Cradle CFD, which we will see later on. So that is basically used for the optimization and for the data mining. And as I mentioned before, these are integrated into different applications. Furthermore, we have Odyssey Explore, and Odyssey Explore is more of an application which is used for data pre and post processing. And hereby, it's so some of the functions which are located, for example, in Odyssey CAE for the post processing of your data. So, for example, heat maps. These can be also found back in Odyssey Explore. Finally, we have the Odyssey FMU Builder and FMU Runtime. And this plugin is basically used to actually run the FMUs that you have exported from Odyssey CAE itself. So as you might think, this Odyssey FMU and Odyssey Solver doesn't necessarily have a dedicated GUI for itself. In today's webinar, as you can see, this is quite broad, and I think we can go along all day talking about what can do what, and we can showcase a lot of case studies around it. But I would like to focus mainly on two particular applications, whereby we have Odyssey CAE and we have Odyssey Solver. So we are going to use Odyssey CAE for the Adams and Odyssey demonstration, and we're going to use Odyssey Solver, or at least Odyssey Solver integrated into Cradle CFD, to tackle basically the problem that we then encounter. In terms of reduced order modeling, which will be later also discussed, some of you might have heard from this, some of you might have not heard from this before, but on a very brief note, just on an introductory setting, reduced order modeling, basically in its simplest form, are high fidelity complex mathematical models. And basically what that means is that if I have a very, very complex model with a couple hundred degrees of freedom, what I want to do then is, if I want to, let's say, use it for real-time applications, which is one of the benefits of reduced order models, I would like to decrease the degrees of freedom such that the accuracy is still somewhat maintained, so that it can represent the main trend line of my response, let's say. This is very, very advantageous, especially if we want to use this, as I mentioned before, in real-time simulation, where you need a direct response from your model itself. And therefore, it makes it also very usable for dynamic responses and dynamic analysis. And another advantage basically is that it can be based, or at least you can create this reduced order model based on either experimental results or even simulation results as well. And as I mentioned before, because we have this reduced amount of degrees of freedom, we have the luxury also that there is not a lot of computational effort needed. So if we, for example, compare it to, let's say, a finite element simulation, so a general engineering simulation, we see that reduced order models are data-driven rather than partial differential equations driven. As you might know, if you have a finite element model, you have a stiffness matrix, you have a partial differential equation for each and every element assigned to. However, when we use a reduced order model, we basically have certain amount of data points that we know. So you have an X, basically, we have an input, and we have an I, which is our output. But I have a data set, and what I want to do then is I want to predict the unknown. And that is basically the whole idea, whereby we predict the unknown in the shortest possible time, so that we can basically be efficient with our work. The power of Odyssey comes then here, whereby we can use any kind of data set, regardless of the source, as I mentioned before. So it can be sound, it can be, for example, a CAD model. It can be also, of course, a response curve, which we'll see later. And this will help you basically to create a relatively accurate model, which is above approximately 5% within your simulation results, and then still manage to represent the accuracy. But on another note, this is done by the fraction of a time, of course. And if we look at, for example, a general workflow, we can see that, as I mentioned before, we have an X variable, which we then basically have to use in our engineering simulation. But therefore, we have to create a CAD geometry, we have to assign properties to it, and then after that, we have to solve it. The idea is basically that this is, and as you might know, and you are an engineer yourself, you know that this can be very, very time consuming, and this can be pretty tiring if you are doing a design iteration, let's say. So if you have to look into different design specifications, and you have to do you have to analyze different kinds of setups, this will cost you a lot of time. The idea with Odyssey is basically to reduce that time, but still be as productive as possible. So what I mean by that is that we have seen now what is the workflow above, But what we want to do with Odyssey basically is to replace that constant manual labor and the iterations behind it. So let's say if I have a data set of 10 different setups, let's say, and I have a response curve to that assigned, I can use then Odyssey to predict 100 different ones based on the data sets or the design space that I have provided to, of course. And this is what this is what we are going to be focusing on today. So in terms of case studies, I want to provide 3 case studies for the audience today. And the first one, what I would like to focus on is a crash simulation from Autoliv. So the idea behind this is that they would like to predict a different design specifications for their seat, and they need to do 2 different simulations. So one of them is a pre-crash simulation, which takes approximately 3 to 4 days to simulate if everything goes right, of course. And this is very, very time consuming. So what they wanted to do is they wanted to basically speed up this procedure. So with Odyssey CAE, the idea was that after 5 training simulations, and what I mean by that is that you have input data from your 5 previous simulations, and then using that, you will train a model in Odyssey CAE itself to be able to predict what is going to be next based on your design settings that you have altered. On another note, this 3 to 4 days has been basically reduced to 160 milliseconds based on those 5 training simulations. So once again, you can see that there's a huge time gain with respect to a conventional engineering simulation, and especially in crash. And another note, on their second node case, with a more complex pre-crash simulation, the simulation time has been reduced to 1700 milliseconds after only 6 training simulations. What does this mean for the actual user is that their computational time has been reduced by almost 97%, which helps them to predict multiple design scenarios. And the actual accuracy of the simulation itself has been within 5% of the finite element simulation itself. On another note, you also have a case study from the medical industry itself as well, whereby reduced order modeling can come into play. So in this case, a podiatrist from the University of Marseille had the challenge to have real-time feedback on the actual effects of an insole design. And the insole design is basically dependent on the actual position of the center of pressure on your foot itself. So what they wanted to do is they wanted to create a reduced order model, which it gives direct feedback to the podiatrist itself, which will then help them later on to alter their design of the actual insole itself. What they have managed to do is that with Odyssey CAE, they have managed to create a reduced order model based on 30 simulations, whereby the actual prediction of the displacement is basically done in less than a second. So once again, for this real-time application of your reduced order model is completely viable. And by this, they were managed to be optimized the inner and the outer sole design of the actual insole for the clients itself. Finally, this case study is from Odyssey AI. So the case study is what we have seen before from Odyssey CAE. This is specifically from Odyssey AI. And Odyssey AI, as I mentioned before, is more a image-based prediction tool. So you can use, of course, different inputs such as sound, CAD models, and images as well. And the idea was basically here to, if you have a manufacturing process, let's say, in this case, the manufacturing of brake discs, we can see that on the top right that there are several pictures which show that the actual part itself is badly manufactured. So there's a manufacturing deficiency in the parts itself. So the idea is basically that if I have a certain amount of data set of pictures, in this case, the pictures of the brake caliper of the brake discs itself. We can then use that to learn via Odyssey AI, basically to train a model, whereby we can then assign, okay, this is a right, this brake disc is right, and the other one is wrong. And by that, you will be able to basically predict with every single new picture what you have from your design process or from your manufacturing process in this case. Is it a good, does it have a manufacturing deficiency or not? But please note that you can always go all out, and you can use always a lot of pictures to train your database, but it's not always needed. As an engineer, especially from a CFD perspective, if I look at it, you can compare this to a mesh convergence study, let's say, whereby if after some time, if I refine my mesh, the actual accuracy won't necessarily be higher, but my computational effort will still increase. So what we can also see is that after conducting multiple images and using it as the learning base, we can see that basically after more than 120 pictures at least, we can see that the accuracy of this identification of the brake discs is at 100%. So the idea is basically that you would sometimes need to make a trade-off that, hey, do I want more pictures for my learning database or less, depending on how accurate you want it to be. But you might think, okay, this is all clear. I think I can live with this, but how does that look like in practice? Because I can imagine now you can see, okay, these are all nice and it's sort of understandable, but how does this look like? So in order to demonstrate this and to basically showcase to you how Odyssey can be used from an engineering perspective, at least, I would like to show you this case study based on a Adams recall model. This is especially interesting also for myself because I've been part from a Formula student team and I've been part of the recall dynamics department. And one of my specific tasks was also to, hey, try to optimize the suspension settings such that if we go over a bump, let's say, we are not going to touch the ground, which can be quite a challenge. You need to create first the recall dynamics model, of course, but then if you have a lot of options, you have a lot of suspension and suspension stiffness settings, let's say, so both for your damper and your spring, then you need to go quite a lot and you need to analyze quite a lot of different settings. So in this case, what we want to do is to basically minimize the chassis pitch after an initial bump, because the actual idea is that we consider a vehicle traveling at a constant velocity, and this goes over a bump. This bump itself has been emulated by Testrix, which has been created in Adams Modeler, and the actual bump itself is basically induced as a step function. But as I mentioned before, in order to actually fine-tune the chassis pitch, we need to use some kind of input, right? So the input in this case will be the front and the rear spring and damper stiffness as well. And what we will consider this basically as the axle stiffness. So what does that mean? That both for the front axle, we have a certain amount of spring stiffness for one wheel. And then that will be, of course, then changed in the Adams model itself. The actual model fundamentals, just to give you a view on it, we have the car on the left, which is basically put on a test rig, and then you can see on the right the actual step function, which is imitating the bump itself, and a couple of information from the Adams model itself. It is basically an Adams transient simulation. The actual simulation takes 4 seconds, and the iteration is 400 cycles, while the vehicle velocity is 8 kilometers per hour, whereby we have a double wishbone suspension with the push rod setup. The actual workflow itself, basically, this is what we are going to follow during the demo. We have an Adams modeler simulation, basically from scratch. Then we have already simulated 10 different setups. So prior to actually using Odyssey CAE, we still need to have some gather some data. So that's what we generate a design space in this case. So we will generate 10 different setups with different kind of suspension settings for both the dampers for the front and rear, and also for the spring front and rear. So we will have 4 different variables. After that, when we have that data, we will import that data in Odyssey CAE, and thereby we can already then see what our response curves will be for the chassis pitch. Then we will try to look at our DOE and how to eventually improve. And then after that, we will perform a optimization study whereby we can obtain the optimal response curve based on the Odyssey solver itself. So without further ado, I think we should go and dive into this. So when you open Odyssey Lunar, this is what we can then see. So this is basically the GUI of Odyssey itself. And just you might be familiar with different engineering tools as well. You need to create a project. So what we are going to do is we are going to create first our project by clicking on the top left here. And thereby we have to specify, of course, our project name. Hereby I will call this demo. And the actual working directory itself, where where all the files will be saved, have to be specified. So that will be basically done if we click on the free button right here. And in this case, I will just going to copy the actual file path, whereby we will basically specify our working directory. You can, of course, fine-tune it for yourself as much as you wanted. So after that, when we have created our new project, this is the next what will open up. So you can already see that from left to right, we are opening up quite some icons. So the first one, what we open up is data. And hereby, we need to import our data set, basically. So as you might remember from the workflow itself on reduced order modeling, we need to have some kind of X variable whereby we have an Y response function to it. So what we're going to do is we need a CSV file for this. So prior to setting up this actual project, you would have to make sure that you have a CSV file of your suspension settings. So what does that mean? If I click on import CSV, you can already see that we have here 2 CSV files already prepared. Very important that it is prepared. The X base case is our input. So those will be our variables. And what we want to vary, as you remember, we want to vary our spring and damper stiffness for the front and rear. So if I click on it, I will import that. And then we can see that we have the front spring stiffness, front damper stiffness, rear damper stiffness, rear spring stiffness, and rear damper stiffness specified. On another note, we can also dive into what we need to actually do prior to actually receive some response curves. We have to specify our Y data, which is our output. And this is done also via a CSV file. So if we click on import data from CSV, we can already see that this is once again already prepared. This is prepared. Hereby, we have the 10 different response curves for the 10 different suspension setups. So if we click on that and click on open, we can already see the amount of data points. However, it is very important to note that in Odyssey CAE, the amount of cases which you have for your Y data and the amount of cases which you have for your X data needs to match. And you can see that the actual setup of this CSV file is technically incorrect. It should be 10 cases of 401 points. And we can do that directly. So let's say if you have a wrong CSV file, which is not working, or it is wrongly set up because of the format, you can just directly transpose it and it would be changed from the 401 cases to 10 cases. And by that, now we have a matching pair. So we have 10 cases for both the X and the Y data. But we have, of course, 401 points, which are the actual data points from for the response curves that we are going to see here. You can click on check data, and by the check mark, it is verified. So there are no errors with the actual data itself. And then by that, we can click on validate data configuration. And by a warning, whereby it says, OK, everything will be deleted. Let's say if you had already some files regarding to it. After clicking on OK, more icons will open up, and we basically get into the Odyssey CAE GUI. So this is what we can see. On the left, we can see the actual response curves of the chassis pitch angle, and we can then also look at the specific abscissa at a specific point, what my regression coefficients will be. Regression coefficients are usually important because it will basically indicate the dominant variable at that specific point. So what we can see, for example, at abscissa 200 is that the front dampers and the rear dampers, at least the absolute value of it, even though if it's negative, it's positive, doesn't matter, those are the more dominant ones. So if you change those variables, those will have the most effect at the specific abscissa. So that is something that you can already look for when you are importing your data. But of course, we can also see the parameter sets, which are defined here. So as mentioned before, we have 4 different variables, and you can obviously choose to use a different kind of let's say front suspension setting. Let's say the front spring stiffness. I want to go to 100,000, and I want to use these data points to actually create a response curve from this. So if I click on the button itself, on the append with this on this arrow, now by using these points, I can create another response curve based on my data that I have provided. And this can be done by clicking on Run. And this will be then the actual response curve then based on what you have imported and based on the data that you have provided here. On another note, what is important to do if you have validation data available, I didn't talk about that yet, but basically validation data is what you are obtaining, let's say, from your experiment or from your simulation itself, and you want to create a reduced order model based on that as well. You can basically then use a comparison study of different interpolation methods, because you have to interpolate first to actually create an optimization study itself. And this can be done via the interpolation button, clicking on the gear, and then going to automatic configuration and selecting compare interpolation methods. And by that, if you have, of course, validation data, which we don't have in this case, you can then basically let Odyssey Pulsar, which is basically the language of the Odyssey Quasar, I mean, which is basically the programming language which is being used by the solver, basically compare different interpolation methods for you based on the data set that you have. This is currently not applicable because we don't have validation data. So another important point which needs to be considered is the actual design space itself. Because when you import your data set, I will just clear this for now. When you import your data set, you have a certain amount of data points scattered around your actual design space. So what we can see here, whereby parameter 1 is the front spring stiffness, parameter 2 is the front damper stiffness, parameter 3 is the rear spring stiffness, and parameter 4 is the rear damper stiffness. We can then see that the actual seeding of these points are not completely equally divided. We can see that, for example, for parameter 1 and 2, we have a lot of data points focused on the lower regimes of the stiffnesses for both the damper and the spring. But we can also see that we have a huge void for the front spring and damper stiffness correlation at higher damper stiffnesses. So what we can do in this case, if we want to know a bit more about our simulation, so what I mean by that is that if we want to basically expand it a bit more with different inputs, we can improve our design of experiment using Odyssey. What I mean by that, you can do 2 things. You can either say, I'm going to add points manually. So I see here is a large void, so I will add it here, or I will add it here, or I will add it here. This is completely on you. You can choose by your own, but you can also say, okay, I would like to do this automatically. So then if you want to do that, you have the opportunity to select a different algorithm. I don't want to go into it too much in depth, but basically you can make a choice for that, and you can specify the amount of points that you want to add to. So if I want to go only with, let's say, 5 different new points in this DOE space, we can then click on Improve DOE. And the new points, as you can see, will be automatically added. But not only to these two graphs, but also on the other types of correlations. So let's say if I have the correlation between the front spring stiffness and the rear damper stiffness, we can see that those points are also added based on the actual addition of the actual improvement of the design space itself automatically. And with that, if you have, for example, if you have your simulation set up, you can save this design space, and then by that you can use it in a parser, whereby the parser we will be extracting those points, extracting the variables, and create new simulations for you. And this is the next point, the final point also that I want to talk about, is basically parsing. Parsing can be done via Odyssey CAE, via heading to Tools, Parsers, and for several applications, for example, let's say LS-DYNA or Nastran, or even NMSCAR, there is already implemented parsers. So the only thing that you need to do is to specify basically your simulation files, specify your DOE, do the extraction, and run the simulations. But of course, let's say if you have a different tool, which is not fine-tuned directly to Odyssey CAE, you can use a generic pulsar. And with the generic parser, which is based on pulsar. With this generic parser, you can basically use any kind of data set or any kind of simulation, doesn't matter which one. You can basically specify your variables from your log files of that simulation itself, and you can connect it with the DOE variables that you have in your CSV file. And by that, you can, once again, already create different kind of simulations automatically. So you don't have to do this job manually after all. But now, as we have come to almost the end of this Odyssey CAE demo, I would like to perform the optimization study as mentioned before. So our focus is to basically reduce the actual oscillations after the initial bump. So after we have an initial bump, we have one bigger bump coming afterwards, and I would like to minimize that completely. That will be my goal. So what I want to do is I want to click on the gear under the optimization tab, and keeping all the parameters at default, I would like to define my optimization problem. What I'm going to do is I'm going to create a new target, and I'm going to rename it to demo in this case. I will keep the weight effect at default by itself, and I will select the minimize value function at a specific point, and which will be at approximately 200 where we are located. What I'm going to do with this is basically I will try to minimize that point at I will try to minimize my value at that specific point of the abscissa, which is at 200, and therefore I expect also to have less oscillations or no oscillations at all. So if I'm going to click on OK, the project has been saved, and this also indicates that I can run my optimization study. And if I run my optimization study, I can see already that the solver starts to iterate for the front for all the variables what we have here. And after a couple of iterations, usually around 100 iterations or so, this comes to a stop, and then your final response curve will be shown. It depends on the case, of course. It can, if you have multiple response curves available, so the bigger your data, the longer this will take, of course. So we can see that the optimization has been finished, and we can see that the response curve obtained is in blue. We can see that this has been minimized, but we can still see that there are still some bumps visible at this point. So by having this done, I think it's also important to show how accurate this is. So if I go back to my presentation, the model validation looks like the following. We can see on the right-hand side, compared to the previous animation, how the response of the car is doing with the actual values obtained from Odyssey itself. And we can also see the comparison with the actual Adam simulation. We can see that from the Adam simulation, the car completely settles, but in Odyssey, we can still see these minor oscillations. The reason for this is because as you have seen, some of the response curves had quite high amplitudes towards the end of the iteration as well, as in the chassis was still unstable. But we didn't have a lot of response curves which were in that specific domain where the oscillations were completely negligible or zero at all. So in this case, what we can see is that Odyssey can still predict relatively accurately the actual trend line which is happening, which oscillates around a mean. But in order to get an exact solution, you would then still have to add some data points in this case. So let's say if you increase it to 15 data points with the new DOE that we have just created, you can remove those oscillations completely, whereby, of course, with the new DOE, you would be then closer to a more flatter curve itself. On the final demonstration, what I would like to do is I would like to present to you how to create a reduced order model using Odyssey again, but then we are going to use Cradle CFD in this case for a heat transfer case. So in this case, what we have is we have a PCB which is located, or at least we have a PCB in a so-called chassis, whereby a CPU is located on, whereby both the CPU and PCB emit heat. And we have a fan velocity at the end, which we will see later, which is extracting all the air from the system. This is basically a closed system. And the idea is basically that we would like to use reduced order modeling to actually simulate different scenarios within a couple of seconds. Here also, as before with the Adams case, we can see that we have 10 different simulations first. So we need 10 different simulations first to actually create our reduced order model. But of course, if you have experiments, you can use that as well. So the actual model itself has been created in Cradle. It's a steady state simulation whereby, as I mentioned before, the CPU and PCB are emitting some heat, whereby we have an outlet fan which has a velocity of 1 meters per second, which replicates basically the fan physics. The material conditions are basically air, which is located in the chassis. The CPU is made from copper, the PCB is from epoxy resin, and the fins are from aluminium. The actual workflow is a little bit different because in Cradle CFD, you have the opportunity to already create parametric studies itself. This has been already created for this for the sake of time, of course. This has been already pre-created. And hereby, we can see also the different settings which will be used. So the fan velocity and the CPU heat source, which will be changing for our reduced order model. This has been also moved into a design of experiment in the CSV file, which can we see below. So as before with Adams, we have an initial CFD model, we have 10 different simulations, we have created this parametric study in SCFlow alone. Then what we will actually do now is create the reduced order model based on the SC solver from SC solver itself. Then we can take a look at the actual results, and hereby we can also look at the influence of the different scenarios. So to actually start, let's dive into the demo. We have SC solver opened here. And normally this is not directly available. You would have to open this up via options, configuration, and going to workflow and enable workflow settings. And by that, this window will appear for you, and then you can click on it, and by that a new window appears, whereby, as I mentioned before, you can create a parametric study from scratch. So this starts from one CFD model, and you create 10 different ones. Or what we are now going to do is we're going to create a 3D reduced order model in this case. So what we need to do is we have to click on the Create 3D ROM, keep everything checked, and click on Next, and finish. By that, a new window appears, whereby we will, just like before with Odyssey CAE, we will specify our base calculation path, which will be here at SCFlow. This is where all the simulations are located from M1 to M10. So if we go to select folder, we do have to keep the calculation folder base name, whereby all the simulation results are located from SCFlow. So all the field file and the log files itself. We do have a DOE as well, as mentioned before, which is in a CSV file format, whereby we have the fan velocity and the CPU heat, CPU emitting heat conditions as well. Then we have to go ahead and extract our response variables. So in the step before, we have added our X variables basically, but now we are going to extract our L variable, our Y variable basically. And this has been done from an L file. So to keep it consistent, we need to always select the first map, and then we will select the log file from scflow itself. Hereby automatically the last cycle has been selected where the simulation has converged. And what we are interested in is the temperature, the maximum temperature. And this can be selected here by a double click. We will call this max temperature. And we will click on add. So when this has been selected, we have now specified based on our conditions, what it will be our response variable, which is then the temperature. If we click on execute, now the actual 3D ROM window is being opened. And now we have to include an actual result file as well. And if you remember, we have selected the first map, which was M1. And hereby we have also, which goes already automatically to it, we have the field file, which basically contains all the actual results from the simulation. So if I click on open, it will recognize the field file for the actual training is the cooling fin model itself, and the actual 3D reduced order model itself will be saved as coolingfin.3dr. You can, of course, select a solver. This is Cradle CFD 2024.2. In the newest version of Cradle CFD, you will have multiple options for the Quasar solver to use it to create your 3D reduced order model. To actually see the results, we have to launch the post-processor after the 3D ROM prediction. And if everything has been set up, we can click on execute. And this actual creation of the 3D reduced order model, it takes a couple of seconds, as you can see, whereby the file has been already created. And on my other screen, SC Post has just opened. And we can see that basically this is the actual creation of the 3D reduced order model, whereby if we click on the actual, for the ones who worked with Cradle CFD before, we click on the actual file, click on 3D ROM, we can already see that the changes, or at least the variables that you want to change, are actually already included. So we can see that the fan velocity can be changed and the CPU heat source can be changed. So let's say if I move my heat source to 17.55 and I move my fan velocity to 0.95, and if I click on first, I can of course show to you how the temperature looks like if I have the M1, so the initial setting. But if I select these ones and I click on interpolate, it will interpolate automatically, and then you can see that there is a change in the actual field, in the temperature field itself, because of course we have used a different boundary conditions for this case. But the same can be done also if I want to decrease to 0.8, and if I want to keep this to 18, and I click on interpolate, then this will happen again. And just for the sake of illustration, you can see that the temperature field has been changed, especially at the back and the begin of the flow field. So also to compare this, I have created a comparison between the 3D reduced order model and the actual verification study. And we can see that the actual temperature field itself is very comparable to each other. There are some minute differences close to the actual fins itself, which we can see, but the actual trend and the values itself are still in a good range within each other. But still, this costs me a fraction of a time, while if you run this CFD simulation standalone, this can take up to a couple of hours if you use a low amount of course. So just to conclude, what did we learn today? So first of all, Odyssey is basically a data-driven design and engineering optimization tool, which basically helps the engineer to overcome, for example, more intense manual labor. So it helps at automation. Odyssey itself consists of multiple applications, such as Odyssey AI, as mentioned before, for image recognition, Odyssey CAE for reliability and DOE analysis itself. And Odyssey technically is very multi-purpose, so it's very, very versatile. We have seen multiple case studies whereby medical industry, crash industry was involved, but also we have seen CFD simulations and also multiple simulations involved as well. And the actual goal with this is basically with Odyssey to help the engineer and improve their design processes and help them with their optimization studies. If you got a bit interested from this, I would also recommend to follow our webinar on the 4th of June, whereby we will look into Odyssey AI as well, but in combination with Romax, whereby Romax is Hexagon's gearbox solution, basically. So if you are interested, feel free to register. We can also include the registration link in the chat as well, but it will be also in the presentation, so you can then register for yourself. And by that, I would like to close off this webinar. Thank you for attending.